I think most people know that AI is powered by artificial neural networks, but I think understanding semantic vectors is almost more important. Semantic vectors are foundational to how AI works, whereas the neural network is mechanistic. A semantic vector means representing meaning as a direction in a higher dimensional space. So from a mathematical perspective, it's just a normal vector, i.e. a list of numbers. The only difference is that we normally care more about direction than magnitude, so we often normalize our vectors to have equal length. Now the semantic vectors used in modern AI are usually between maybe 1,000 to, I think sometimes more than 10,000 long. But we can imagine it in 3 dimensions to try and understand how it works. So if we have a semantic vector space in only 3 dimensions, normalized vectors, which means they have equal length, will look like points on a sphere. So we can imagine ourselves standing in the middle of a sphere with points all around us in a sphere. And in a real semantic vector, it would be multiple dimensions, which means it would be called a hypersphere. But anyway, so let's imagine we have apple, orange, and pear. These are going to be clustered in a certain area because they're all fruits. And then we might have emotions over here, like happy, sad, excited. And then somewhere we're going to have adjectives like big and small, etc. So similar concepts cluster together. So how do we handle things that are opposites? So it's interesting to think about the difference between something being opposites versus being unrelated. So the word apple is very far away from the word happy in semantic space. But they're not opposites, they're just completely unrelated. So they're going to be on completely different parts of the surface of our hypersphere, but they're not opposites. Opposites or antonyms are words that sit on the same semantic domain but differ in one property, yeah, so big and small sit in the same semantic domain because they're both adjectives pertinent to size, but they differ in property, right? Yeah, so when I was first learning about semantic vectors, I imagined that antonyms would sit at opposite sides of the sphere, or at like the opposite poles, but that isn't true at all. So words like big and small are clustered together, very close together, but they're sort of smeared across the surface of the sphere. So you might have, say, gigantic, big, medium, small, tiny, all sort of spread across. So they're clustered together, but spread out. So let's imagine we want to represent the semantic of a large cat. So we could start off with a separate vector for cat and a separate vector for big, and then we can just add them together into a single vector. We don't need 2 separate vectors. So yeah, we take the vector for each of cat and big and add them together. So when we say we add them together, literally, so each vector is a big array of numbers. We literally just sum every number in each vector, element-wise. Very simple addition. So this gives us a new vector which, if we were to plot its position on a hypersphere, it's basically halfway between the position of the vector for the word big and the vector for the concept of cat. I should just add here that the semantic position of the word big is slightly different than the semantic position of the concept of big, because words don't necessarily always map exactly to concepts for a variety of reasons. I mean, a word can have different meanings in different contexts, obviously, but that's a digression. So what if it's a cat of unspecified size? So a cat of unspecified size is not the same as a cat of size medium. We can think of it as like a triangle, right? So if the concept for cat is here on our hypersphere, and then we've got like big, medium, small across here. So think of it like the concept of cat. So if it's a big cat, it gets sort of dragged over towards big. Or if it's a small cat, it gets sort of dragged over towards small. A medium cat would be like here, right? But it's not in the same position semantically as a cat with an unspecified size. So a cat of unspecified size is actually semantically distinct from an average sized cat. Anyway, so yeah, the problem with three-dimensional semantic space is that there's many properties a cat might have. It can have different colors, it can have a temperament, different ages, right? So on a three-dimensional sphere, we simply don't have enough space to have all of these different properties apply to our cat. We would get collisions, right? So you would, your vector arithmetic would just create all these collisions where you'd add your two vectors and get some weird results where you'd end up with completely the wrong semantic. Anyway, so this is why the semantic space that's used for AI has thousands of dimensions, because it means our sphere has a huge amount of surface area, and we can add a huge amount of concepts together. It's important to point out that semantic vectors are not only used to represent the meaning of individual words. Yeah. So I mentioned that earlier, right? So you can plot the semantic meaning of any word on the dictionary, but there's also semantics for combinations of words. There's also different semantics for the same word. There's a semantic for an entire paragraph or an entire book, right? So yeah, the composition of words into sentences, paragraphs, and even an entire book create unique semantics. You know, so the semantics of a book might hold the concepts of, like, I don't know, this book is about friendship and adventure or whatever. Although obviously if you try to put lots of concepts in a single vector, you're going to sort of dilute it, but we'll touch on that in a minute. Hence why large language models use huge vectors, yeah. Cool. Right, so where does a neural network come in? So a neural network is basically a giant program for manipulating semantic vectors. Pretty much everything the neural network does is just vector arithmetic. So think of it like this. So let's say that we have a calculator for doing maths. Well, the data it processes is numbers, and the calculations it can do are like, you know, plus, minus, multiply, divide. Think of a neural network as like a calculator for semantic vectors. The data that goes into it is always vectors, and the operations it performs is vector arithmetic. Right, so I'm going to demo some vector arithmetic, so if I can figure out how to share the other screen. So I won't go through the code, but basically, so what I've done is I've used a small AI model, an embedding model, to create semantic vectors for every word in the English dictionary. And I have functions to add and subtract vectors and a function for searching for the most similar vectors. So I don't know if I've loaded this namespace. Looks like I have. Right. So I'm just going to load my embeddings. Semantic vectors are often called embeddings. I don't know why people call them that, but semantic vector is more informative. So the structure is like this. We've just got pairs of words with, where it says object f, whatever the hell this is just our vector. It's just the data structure that it's using. I could show you the contents of the vector, but it would just be a huge list of numbers. Anyway, so most similar allows me to just show, you know, what are the most similar words to this. So most similar words to cat is obviously cat itself, cats, catting, feline, etc. Most similar words to happy. So yeah, this isn't particularly surprising. This vector similarity is how you implement a search. So like, for example, my photo gallery, I implemented a image search, right? So I've used a model that creates a shared semantic space between text and images. And yeah, we just use cosine similarity to figure out which of the vectors in our database is the most similar. But anyway, where things get interesting, so this king minus man plus woman is the classic example that people always give of vector arithmetic. So we'll evaluate that, and it gives us queen. So why is that? So, well, it just means that if you subtract the vector for man from king, I suppose you get some sort of vector that maps approximately to the concept of monarchy or whatever. And then you add woman and it gives you queen. So to be clear, king minus man plus woman doesn't exactly equal queen. This is a similarity search. So the vector that we get when we subtract the vector for man from the vector for king and add the vector for woman is the most similar to queen. And we can do it. So Paris minus France should give us the concept for capital city. And then we add Germany and it gives us Berlin. So yeah, we could go through all these examples, but they're all pretty much similar. So jumped minus jump plus walk should be walked, and it is. Anyway, so, but where things get really magic is when you add multiple vectors together, because you can actually save multiple semantics in a single vector, which is like black magic. So I'm going to look back at my script here. Where did we get to? Yes. So because a neural network has so many dimensions, we can actually add semantic vectors together and get a new vector, which represents the value of both. So it's like a crazy black magic because you've put more semantics into the vector, even though it uses the same amount of space in the computer's memory, right? So the vectors we're using here, I think Qwen3 embedding, which is the model we're using, I think it gives us 4,096. We could check, but it's about 4,000 dimensions, right? So we've got 4,000 numbers. Anyway, so we can add the vectors together, and we just get a vector of the same size, but it has more information in it. So if we do king plus apple plus rock, I don't know. Yeah, so we can see it still contains the semantic meaning of rock and king. So apple has been lost, right? So presumably the semantic for apple is still in the vector somewhere, but it's sort of diluted. So, because remember, this is a similarity search, right? So we're creating a single vector, which is basically a superposition of the vector for king with the vector for apple with the vector for rock. So really it's a sort of kingy, appley, rocky vector. And when we do this similarity search, these are the top 5 words that come up. So if we do a similarity, so if we do king plus big, sorry, cat plus big plus hungry. Yeah, so all of those have been preserved. So this is crazy, right? This is one of the most important things that you can do with semantic vectors, is you can just add them together and basically it's basically an incredibly powerful form of compression. A semantic vector is basically just a single point on a hypersphere. So just to re-emphasize this again, right? So maybe cat is here on a hypersphere, and big is over here, and hungry is over there. All we're doing is making a new point that's pointing at exactly that spot in the middle between them. And because we have so many dimensions, so there's not any collisions happening in semantic space, so it's able to encode all of these concepts in a single vector. Very important concept. Let me just look at my script again. I think that's my demo done. So you might ask, so let's imagine we want to encode the concept of a cat attacking a mouse. How would we encode which animal is attacking which? So the short answer to that is basically that order can be encoded in semantic space as well, using rotation, you can rotate vectors. So I'm not going to cover that in this video, but you can research ROPE, which stands for rotary positional embedding. You apply a slight rotation to every vector as you work through, and the large language model has learned how to recognize that rotation. So everything I've shown you in my demo is basically just parallel tricks, right? None of them are useful by themselves, but these are the calculations that power AI, such as large language models. So a large language model like that which powers ChatGPT or Claude or Gemini does trillions of vector operations to answer a single question. I'm pretty sure it's trillions. So first it needs to calculate contextual semantic vectors for every single word. So because words mean different things in different contexts, it needs to work through every single word in the input and calculate a contextual semantic vector. So that's, what does this word mean in this context? And at the same time, it builds up this thing called a residual stream, which is basically the LLM's thought process. So as it's doing that, it's basically just adding semantic vectors over and over. So basically at each step, at each layer of the neural network, it adds another semantic vector, creating a superposition of basically, so if each layer of the neural network has a certain impression of the data it's looking at, it adds them all together. So if AI has consciousness, which some people think it does, then that consciousness would presumably be in the residual stream. It's a superposition of hundreds of semantic vectors all combined together. Now a large language model obviously predicts one word at a time, that's how it works. Every pass through the neural network from input to output produces one word or one token. They're called tokens technically, but you can think of them as words. Casting shadows. So this is one of those things where AI is teaching us a lot about neuroscience and just the nature of intelligence in general. So why is it that so much information can be encoded into a vector of a few thousand numbers? Well, it's because a hypersphere in multiple thousands of dimensional space has an insanely enormous surface. So we can point our vector exactly in the middle between king and apple, and it's unlikely to accidentally fall on top of another concept. But if our AI's thoughts are all done in higher dimensional vectors, how does that help us create language? So basically the best analogy or what's the word? Metaphor to think about it is, it's like how a higher dimensional structure can cast a shadow onto a lower dimensional plane. So if you were to make a cube out of matchsticks and then shine a light through it onto a piece of paper, the shadow of that cube would look like a cube, even though you've taken away the extra dimension. That's kind of what it's like. So English language, so language is, it's linear, it's nested, so it uses nested structures, but it's linear, and we've got a finite number of words. So someone with a very large vocabulary might know 50,000 words, and most people don't use that many words commonly. But anyway, I mean, semantic space has, I don't know, trillions of trillions of trillions of trillions of trillions of positions on the hypersphere, just an unfathomable number. But despite how big our semantic space is, we can basically cast a shadow of that onto a lower dimensional structure, and that's what language is. Language is evolved to help us represent a high dimensional structure onto a lower dimensional plane, basically. A sequential output format. Yeah, so that's it. So I was going to write up a list of terms. Don't think I really did a very good job. So semantic space or vector space. So what we're talking about here is just that higher dimensional space that we're using to store vectors. and our hypersphere is basically if our vectors are normalized, which they are in a lot of contexts, because we care more about the direction that the vector is pointing in than its strength, then we can plot it as a hypersphere, and the hypersphere makes it easy to think about, right? Yeah, so that's it. The code for my demo, I will post a link to it on, I'll put it on GitHub and post a link to it.